Imagine standing inside a furnace heated to 1500 degrees Celsius. At this temperature, structural steel doesn't just get hot, it turns into a glowing liquid soup. Now imagine that inside this very furnace, a machine is spinning at 15,000 rotations per minute, withstanding forces that would tear a skyscraper apart. This isn't a sci-fi nightmare. This is the everyday reality inside the core of a modern jet engine. Every single time you fly, the turbine blades right behind the combustion chamber are exposed to temperatures that are hundreds of degrees hotter than the melting point of the metal they are made of. By all the laws of basic physics, these blades should deform, melt, and cause a catastrophic engine failure within seconds. Yet they survive for thousands of hours of continuous flight. How is this physically possible? Today we are stripping away the titanium housing to uncover the impossible engineering and secret cooling systems that keep commercial aviation from melting out of the sky. To understand the scale of this miracle, we have to look at the brutal mechanical forces at play. A single turbine blade is about the size of a human hand, but when the engine is at full takeoff thrust, it spins so fast that the centrifugal force creates an effective weight of several tons on each blade. It is the equivalent of hanging two fully loaded semi-trucks from a piece of metal the size of an iPhone. Combined with the 1600-degree volcanic gas hitting them directly, the metal faces a double threat: extreme thermal stress and immense mechanical tension. The first line of defense against this destruction is single crystal casting. Standard metals are made of billions of tiny microscopic grains. The boundaries between these grains are weak points where heat and stress cause the metal to stretch and crack, a deadly phenomenon known as creep. Engineers at Rolls-Royce and General Electric solved this by growing an entire turbine blade from a single continuous crystal of metal. To make it even more heat-resistant, they alloyed the nickel with rare exotic elements like rhenium and ruthenium, which cost thousands of dollars per kilogram. With no grain boundaries, the blade becomes exponentially stronger. On top of this single crystal structure, they coat the blade with a specialized thermal barrier coating, a futuristic ceramic layer just a fraction of a millimeter thick. This ceramic acts exactly like a space shuttle heat shield, dropping the temperature at the metal's surface by up to 300 degrees. But even a ceramic shield cannot fight an open inferno forever. The metal still needs to actively fight the heat. The real masterpiece of survival is hidden inside the blade itself. If you cut a modern turbine blade in half, you won't find solid metal. Instead, you'll see a complex labyrinth-like maze of tiny serpentine cooling passages. This is the active jettison of heat, powered by bleed air. Remember that high-pressure air compressed at the front of the engine? Before it ever reaches the combustion chamber to be set on fire, a small percentage of this relatively cool air is redirected around the inferno and pumped straight into the roots of the spinning turbine blades. To force this air through a blade that is spinning at over 15,000 revolutions per minute, engineers have to exploit the laws of fluid dynamics. The air entering the base of the blade is under immense pressure, packed tightly by the engine's compressor stages. As it rushes into the internal channels, it encounters a brutal obstacle course. The walls of these tiny internal microscopic pathways are intentionally lined with miniature ridges called turbulators. These ridges disrupt the smooth airflow, forcing it to tumble and swirl in violent eddies. This chaotic turbulence is a deliberate engineering choice, drastically increasing the contact area between the cold air and the hot metal, tearing the heat away from the core of the blade at an astonishing rate. But the interior geometry gets even more sophisticated near the trailing edge of the blade. Here, the space becomes too narrow for serpentine channels, so engineers implement a matrix of tiny cast metal pillars and pin fins. As the heat-soaked air forces its way through this dense forest of microscopic pillars, the surface area for thermal transfer skyrockets. Simultaneously, these pins act as structural reinforcement, preventing the incredibly thin walls of the blade from collapsing under the immense external pressure of the combustion gases. It is a dual-purpose masterpiece, a high-efficiency heat exchanger and a rigid structural backbone, all contained within a space no thicker than a coin. The ultimate driving force behind this entire internal cooling network is a delicate, high-stakes game of pressure differentials. The cooling air inside the blade must always remain at a higher pressure than the volcanic gas rushing past it on the outside. If the internal pressure drops even for a millisecond, the 1600-degree combustion exhaust will instantly reverse the flow, backfiring into the cooling holes and melting the blade from the inside out in the blink of an eye. Aerospace engineers must meticulously balance the compressor output to ensure that a steady, unstoppable wave of high-pressure cool air is constantly losing its heat, while aggressively pushing outward against the surrounding firestorm. This air travels through the internal maze, absorbing heat from the inside of the metal. But the true stroke of genius happens when the air exits the blade. Engineers use advanced lasers to drill thousands of microscopic angled holes across the surface of the blade. The precision here is staggering. If the angle is off by even a fraction of a degree, the system fails. As the internal cooling air is pushed out of these tiny holes, it doesn't just blow away into the exhaust stream. The aerodynamic forces of the passing gas grab this cool air and spread it flat across the exterior surface, creating a microscopic boundary layer. This is what aerospace engineers call film cooling. This film of cool air acts like an invisible protective glove wrapping around the entire blade. The 1600-degree volcanic gas never actually touches the metal. It rides on a cushion of high-pressure bleed air. The blade is literally insulated by a shield of cold air, running just inches away from an open inferno. It is a continuous dynamic battle between absolute heat and precise airflow. Ultimately, the fact that jet engines don't melt is a testament to the absolute limits of human ingenuity. It proves that in engineering, boundaries are meant to be pushed. A turbine blade is not just a piece of shaped metal. It is a microscopic fortress, utilizing single crystal physics, ceramic shields, and laser-guided aerodynamics to achieve the impossible. Next time you look out the window and hear the roar of the engines on takeoff, remember, you are riding on a machine that defies the very temperature of its own destruction. You are flying on the back of an engineering miracle that keeps its cool in the middle of hell. What do you think? Does knowing the extreme physics inside a turbine make you admire aviation engineering even more? Or does the idea of flying next to a 1500-degree inferno make you a little nervous? Let us know your thoughts in the comments below. If you want to keep breaking down the impossible systems of the world's greatest machines, hit that subscribe button and turn on notifications. The engine is running and we have many more secrets to uncover.